Let's go on a carnival ride. So I know that my artist work is fantastic, so you can tell exactly what's going on here. I need a smiling face because we're on a carnival ride. If you've not heard of these are called rotor rides. And so what happens is you get on there, you walk into this ride, and it is this circular or this round kind of containerish thing. And so you and all your best friends line up against the walls. And then this thing slowly starts to rotate and picks up speed. And then all of a sudden, they drop the darn floor out of the thing. So the only thing holding you there is your contact force with the wall because of the force of friction. Ooh, physics. Okay, so how does this look? Let's do a side view in case you're not quite sure what this looks like. And here is, that's a horrible, okay, I can't even draw stick figures. That makes this really sad. Okay, there we go. So I'm trying to make it clear that my body is in contact with the wall and that I'd be looking at this like straight down. There's no floor beneath my feet anymore. So what kind of forces do I have going on there? Well, let's see, I have some sort of center-seeking force this way. Let's see, and then some of the oldies but goodies are still around. I have the force of gravity straight down, because we're going to leave this just kind of laying in the plane. We're not going to rotate it or rotate it up at an angle and have these things doing different things just yet. We'll leave it nice and straightforward. So I have the force of gravity going down. Well, let's see. I have some sort of force center accelerating this towards the center. So having just one force that way is fine. I need to have a net force. So I'm good with that. But what direction is friction? This is asking about friction. Well, let's see. If friction is going like in opposite direction of the force center, which would be really weird because, yeah, the wall is then doing something odd there. Then all of a sudden I have force gravity accelerating me down. I'm falling. That's a bad idea. So I have to have something that's keeping me suspended. Well, that thing that's keeping me suspended is the force of friction. And we can remind ourselves, we can be like, okay, so I have these two forces here. So I have something counterbalancing the force of gravity. Good. That keeps me from falling or shooting up into the sky. And then I have the center-seeking force. Well, the only thing I don't have listed here is the force normal. So the force normal is my center-seeking force. So let's think about that. That is the contact force between my back and the wall. A contact force between my back and the wall. That is the force normal, and it's pointing in. If I had another force going this way, I wouldn't be going in a circle because I would have equal and opposite forces, and therefore a no net force pointing towards the center of the circle. I have to have a net force pointing towards the center of the circle. So now I can do my sum. Let's see. Let's go up and in as positive. So I have my sum of forces in the y. Let's just start that way. So I've defined up as positive, so force of friction minus the force of gravity. Now this is so I stay put, so I'm not flying up in the air, I'm not plummeting down. So this hopefully equals 0. Now the sum of forces in the x, so I can remind myself, that is the sum of my center-seeking forces, which is just, let's see, to the right I've defined as positive, so force normal equals, this is my center-seeking acceleration. Let me do my little c there. So this is mv squared over r. Okay. So I can rewrite this. It asks me for something in terms of the coefficient of friction. So I need something from this. So I get force of friction equals mg. Where? Whoa, that's kind of like odd. But that's just the total force. So let's see. This thing has the force normal. So I need to get something to relate these two quantities to one another. mg does not equal the force normal because the force normal is going in. The force normal equals this acceleration piece, not mg, so I can't set those two things equal. But I have a definition that says just prior to sliding, that the force of friction equals the force normal times mu. So this is just prior to sliding or after I'm in motion. So this holds true for this because we just want the mu for me just not to fall. So any smaller than that, and I am going to fall down. So I have this. So I can use this definition. I can rewrite this sum from my y. Rewrite the sum from my y. What do I get? I get the force normal times mu equals mg. Okay, I don't have the force normal defined in and of itself, but I have a normal here. So if I move this mu over here, I can make this substitution. So I can rewrite this again, that the force normal equals mg divided by mu. Definitely not just weight, because that would be just weight. So these two things definitely don't equal what you're used to if something's on flat ground. But now I look at this, and I look at this. This is the equation that I wanted to solve because I have a rotation, so I have a frequency. So I can solve this to figure out what that mu needs to be. So now I can make this substitution over here. So let's see, I have mg divided by mu, that's my first normal substitution, equals mv squared over r. And this is where I'm like, okay, I wasn't given the mass, but I don't need it. It canceled. So what am I trying to solve for? I'm trying to solve for mu. So let me rearrange this. I'm going to move the r up here, move the mu over here, and move the velocity down. So I end up with g times r divided by v squared equals mu, moving mu up. Just cross multiplying there. Then I look, and I was given it in terms of frequency. So now hopefully this is starting to seem a little more familiar to you, that we can write velocity equals 2 pi rf. And I've been given the frequency. I have the radius of the spinning ride. So I can go g r over, let's just go ahead and square this, 4 pi squared r squared f squared equals mu. Cancels out. So now I get one final pretty equation that says, so mu is going to equal g divided by 4 pi squared r frequency squared. So let's see what that is. So I have 9.8 is my g divided by 4 pi squared times the radius is this 5 meters times the frequency, that's 0.5 rotations per second. It's in seconds, so I'm good. So 0.5 seconds to the -1. So see, I have meters per second squared. Ooh, square that. See, I wrote it here, then write it here, meters per second squared. This mu, don't forget, needs to be a unitless quantity. So I knew that that seconds needed to cancel out. Let's go ahead and write this, meters per second squared. So these things needed to cancel out. This seconds is to the -1, which in essence pops it up top. So even though this is on the bottom of the fraction, these 2 seconds will cancel out. And let's see, I have r meters per second squared, so r to r, this is not squared, the meters, so those cancel out, and this indeed does leave me unitless, which is good. So, drum roll please, 9.8 divided by 4 times pi squared times 5 times 0.5 squared. Yep. Says that my mu needs to equal 0.199 for me not to fall. Cool.